So of course we had the lab on testing, so you're a little familiar with it at this point, but I was showing you, we're effectively using the equality operator here. Like if I'm testing the absolute value function, which we don't need to write because it already exists, and we know it's correct, and obviously we don't need to test it because it's safe to assume that something in the standard library is written correctly and tested already for us. But we can write our test by saying assert, which is the keyword that says assert some Boolean statement, some expression that can be evaluated to a single Boolean value, either true or false. If the assert, and then whatever the expression is, evaluates to true, then that line just carries on as if everything's fine. If that expression fails, meaning if we say assert false, the program crashes. And it's better to have code that doesn't run that's incorrect. Or it's better to have incorrect code not run than to have it run and you think it's working. It's better to know that it's broken. So here we have absolute value of 5 is 5, absolute value of negative 5 is 5, and the absolute value of 0 is 0. I could test does 6 is 6, negative 6, 6, negative 8, 8, 8, 8. I could, but that's a little overkill. It's not necessary. I've already kind of covered my bases with a positive value, a negative value, and 0, because 0 is kind of a funny one. So, you know, it's a bit of an art to know how much to test. It's a skill you develop. There's no real hard and fast rule. Just try to catch all of the different particular cases. Like if it works for positive numbers, I have no, like a positive number, it's reasonable to assume that it works for most positive numbers. The only way that could start to become a problem is if I were to do something like, well, here's a broken absolute value. And here I see like it fails on a negative number, and that tells me something. Oh, it failed when it was negative? Well, why? Oh, I forgot, right? Yeah. It would be really weird, and we're about to look at this. It would be really strange for it to be like if x is equal to 8, otherwise return like x. Like if it worked for the positive number, it would be really weird for it not to work for positive numbers in general unless I had some really funny stuff. Now this is a contrived example, it's rather silly. It's possible that it could break under funny conditions. But here it's such a simple function, it's reasonable to assume that it's going to work just fine if it works for a positive number. Chances are it works for positive numbers. But here we see it breaks for negative numbers. Obviously this is a broken absolute value function that we're using to show you what happens, but as you can see, the first assert passed, the second assert failed. And at this stage, because the program crashes on that second assert, we actually don't know if the third assert will pass or fail yet. We'd have to fix the second one in order to know if the third one would work fine. Yeah. So, any questions about what you just saw? So here's the example with the square of sum. Whoop. For the sake of brevity, I'm going to get rid of the doc string. But here we go, square of sum. A plus B, C times C, return D. And we have some tests here. I wrote some arbitrary tests. Zeros, a positive and negative, two positive, two negatives. That's probably fine. You might say, well, why not do a negative and a positive? Oh, yeah, okay, fine, fine. You might be wondering what the hell's going on with that last assert. It looks a little different. There's no equals equals. And we talked about this in lab, but it's because computers suck at decimals. And like I showed you in lab, I'll show you right now. We all know that 1 plus 2 equals 3, right? That's obviously a valid statement. And we obviously all know that 0.1 and 0.2 is not equal to 0.3. This is obvious, right? Now, okay, I'm being silly. You look at this and you're like, what the hell? No. Why is it false? Well, let's see what happens actually. Like, well, okay, if it's not equal to 0.3, what is it equal to? It's equal to 0.30000000000000004, obviously. Right? We all know that. Well, no, this is ridiculous. And it's because computers suck with decimals. Whether we like it or not, they do. And it just comes down to the fact that there's so many decimal numbers and we have such a limited amount of ability to represent unique values inside of a computer that the computers have to do some like tricks on how to represent these floating point numbers. And one of the tricks is to cheat a little bit by not even trying to represent all the numbers, but we skip some. And from this you can kind of see, well, it looks like 0.3 may have been skipped because we can't represent 0.3, we can represent 0.3000004. Which is ridiculous. So here, when I checked 0.1 plus 0.2 equals 0.3, it failed, not because it's not equal, but because Python's wrong. Due to Python's limitations, it just can't represent 0.3 correctly. So we're in trouble. The way we deal with this is, it might not be obvious at first, but I'll show you how we deal with it, and then you're going to go, oh yeah, okay, obviously. If two numbers are equal, what's their difference? 0, right? If two numbers are in fact equal, then their difference, like number A minus number B, should be 0, if they're equal. But we can see that there's going to be these issues here with floating point numbers. Now, when a computer can't represent a floating point number, it's always going to be wrong by just a little bit. A very small amount. An amount close to 0, but not 0. Right? We could see 0.0000004. It's not 0, but it's pretty damn close to 0. It's such a tiny number. It might as well be 0 for us. So the trick when dealing with floating point numbers is to never compare them directly with equals equals. Don't. Just don't do it. There are cases where it will work, but I mean, you're rolling the dice. So what you do is you take the absolute difference and check that the absolute difference between the numbers is sufficiently small. How small? It's up to you. So what I would say is 0.1 plus 0.3, well, we'll take the absolute difference of that, meaning I don't really care if it's a positive or a negative, whatever. I just want the absolute difference. Oops, no. I'm jumping the gun here. So I'll take the absolute difference because I don't really care if it's positive or negative. I just want the difference, the absolute difference, to be itty-bitty. So if I hit run on this, we'll see that the difference is, oops, there we go, is 5.5 times 10 to the negative 17, some ridiculously small value. Now you might be wondering, wait, I saw a 4, not a 5. It's because Python was kind of just cheating and not showing you all the decimal places. It was just being like, 0.0004. The difference was actually smaller than that. It's just how it showed it to us. Times 10 to the negative 17. That is a small number. Hilariously small. So if the difference is less than, I don't know, 0.000001, then we'll say, yeah, they're the same. Students always ask, well, what should that threshold be, right? So on the right, we'll call that the threshold. If you want to get fancy, we'll say epsilon, which is a way to say like an itty-bitty little number. What should that threshold be? Well, that really depends on you and what you're doing. If I'm measuring, like if I have a stopwatch that's capable of measuring to a millisecond, right? So 0.000, that's definitely more than enough, right? Because I couldn't even measure anything more precise than 0.000 anyways, right? So like it doesn't really matter. The question you have to ask yourself is, like if you're looking for a rule of, well, what should I set the threshold be? Ask yourself that question. What are you measuring? It's up to you. Are you measuring the density of Starbucks? Oh, if you measured yours and the density came up at like 1.2345, and somebody else measured theirs at 1.234567, are they different, or are you going to be like, it's the same? Yeah, it's the same. Like, at what point do I really not care anymore? That's really what I'm going to say the threshold is. I could make it more precise, right? But then again, we'll know that there will be a point where it will be false because we know the different situation. But what do I need it to be? Really depends. Maybe that's good enough for what I got to do. If I'm measuring volumes of liquid with an instrument that can only measure up to like milliliters, I don't need to get more precise than that, right? That's good enough. So there's no hard and fast rule about how precise we need to be worried, like how precise we got to be. It's up to you and what you're doing in the context and how you're doing it. Let's make sure I'm not frozen. Of course I am. There we go. All right. So that's why I said get the squarest sum of 2.2, 2.2. Just make sure the difference between what I expect it to be and what I actually get is less than 0.001. Why? Because good enough for me. Cool? Any questions about this? All right. Awesome. Whoop. All right. Yeah, that's just that. Yeah. The above tests do a good job at kind of catching different scenarios. And that's what you want to do with your tests. You're obviously not going to be able to test every possible combination when you're dealing with integers because there's an infinite number of combinations. So you just want to make sure you've got like a good variety of combinations of things that you can test. Yeah, like why didn't I test a square of sum 5, 6? Well, I could have. And why not test -1, 1? You're right, I could have, but like it wouldn't be bad to include those tests, but it's probably overkill. Figuring out how and what to test, again, like I said, more of an art than a science. So here's some tests for Celsius to Fahrenheit, right? Arguably, for all of these, I should be maybe comparing, doing the absolute difference strategy. Maybe I should, but I did it like this here. Is this sufficient? Probably. I got 0, a negative number, another negative number, 30, some arbitrary floating point numbers. It's probably sufficient tests. If you're looking at this and going like, if I were doing this, I would have tested this case. Fine, good job. That's fine. This is probably fine. I'm sure someone can make an argument that there would be more or different or better numbers to test as well. But this is probably doing the trick. Here you see I've got 0 when I know they'll be the same. So 0 is always a funny case because it's not positive, it's not negative, it's in between. So that's a good case to check. I want to check a positive number, I want to check a negative number. -40 is a good one to test because I know that -40 in both Celsius and Fahrenheit are the same value. It's basically where the lines cross. So that's a good position to test, and then some decimal values because, yeah, there we go. Cool. 0.001. I figure if mine comes back different with more decimal places, I don't care. That's good enough for me to be like, yeah, it's correct. Okay, it needs to be. Okay, like I said, it really does need to be emphasized how important testing is. If you write a function, you're not done. You have to write a function and then test it. If you don't have tests, I don't want your function. Now, like in assignment 1, I give you the tests. So all you really need to do is write your function such that the tests I give you pass. And I'm going to warn you, the tests I gave you are probably correct, Every year you get someone being like, I wrote the function and your tests are wrong because it keeps failing. No, I think your function's wrong. I might mess up every once in a while, but I'm pretty sure that these tests that I gave you are correct. So you just got to write your function. If all the tests pass, you're good to go. At this stage, I'm not expecting you to be experts in writing tests. What I want you to do is get used to writing tests. I give you the test for assignment 1 because it gives you feedback to make sure you know you're doing things correctly. But make sure you're not just like writing your code, hitting run, test pass, good, move on. No. Look at the tests, understand the tests. Why did I write those tests and not other tests? Take a moment and understand why those tests are the way they are to learn a little bit more about writing tests. Also, a strategy I've seen some students do, so a couple years ago I introduced the tests on the assignments for people to see if they're right or wrong. I used to not do that, but I started doing it a couple years back. But one funny thing started happening. In general, it was really good. The students did better when they would get the immediate feedback if their tests are right or wrong. Because if you hit run and 3 tests pass, but the 4th one fails under a special condition, it lets you know, oh, it didn't work with a negative number or something. So clearly I need to go figure out what's wrong with negative numbers in my function. It works for positive, but what's wrong with negative? Like it gives you feedback on where and how your function might be incorrect. But what I've seen, so in general, it's good for students, but there are some types of students where it's actually made them way worse off. So most students, it helps them, but some students, it hurts them. Because what I've seen happen is students will write their function, hit run, test, fail. They don't even look at what happened, and then they just change it, run, fail, change, run, fail, change, pass, move on. And they have no idea why. Yeah, don't do that. That's a bad idea. You won't learn anything. That's foolish. So make sure you're taking your time. They're there to help you. Automated testing. So I want to be very clear. The tests we have written, those assert tests, are fantastic. A lot of the automated testing that programmers use are built on what we're doing right now. As we learn more, the way we're writing these tests will become a little too limited in order to really do a better job with testing as our code gets more and more complex. We could still do it, but it'd be a giant pain in the ass. But don't think that this is like a cheesy, corny, childish way of doing testing. No, it is sufficient. It is great. But as time goes on, we will learn more sophisticated ways to test because it gives us a little bit more tools and flexibilities on how to test, such that we don't need to write a billion tests. We can just kind of like automate how the tests are done in a good way. We really like this. We're going to learn this later in the semester because there's quite a bit more we need to know in order for us to wrap our heads around how to use these tools. But also, we don't need those tools yet anyway, so that would be a waste of time at this stage. So these are fine. They are not cheesy, they're not useful, they are absolutely great. But 2 common testing frameworks for Python are unit test and PyTest. We will use unit test because it's like really built into Python. PyTest is an external library, I believe, and requires a little bit more setup. So arguably it's easier to use, but it requires some setup, so we don't want to do it. Unit test is nice, it's fine, it's good. So we will use these later. And these are the types of tools that programmers use, like actually. Not like, oh, here's a tool we use for learning. No, I try to avoid that as much as possible when teaching programming. I want you to use the tools that programmers are actually using. I don't want to give you like little plastic tools like you give kids. No, I want you to actually get experience using the real things. Now, type hints. Type hints does a pretty good job at figuring out what the type of the data is. But it's not foolproof, and mistakes can happen. One of the bigger criticisms about Python that people have, myself included, is it's really not that strongly typed of a language. This is an idea that's hard to explain at this stage because we haven't seen other programming languages that are very strongly typed. But basically, in other languages, you have to be very explicit about the type of every piece of data. And if you write code in another language, like Java, for example, that says add an integer and a string together, Java won't even start running. It'll say, what the hell are you doing? It's not like it's going to run and crash. It won't even start running. Python, on the other hand, will be like, great, okay, and it runs, and then when it finally gets to the line of code, maybe it's line number 758 million, and it finally tries to add an integer and a number, it crashes. Where Java wouldn't even start running, and it would go, no, right there, what the hell are you doing? Fix it. That's a good thing. We really like that. And it's funny because, raise your hand if you're thinking of taking 162. I can't stress enough, so much better than this course, and this course is great. A lot of programmers, when going from 161 to 162, get frustrated by how strict Java is with typing. But trust me, you'll only be annoyed about the strictness for like a week, and then after a week you'll be like, oh no, this is good. It saves you a lot of pain and suffering from future you. It's great. Python, on the other hand, it's a little loosey-goosey. You want to add a string and integer? Okay, let's see what happens. Well, it ain't going to work. It'll crash, and it's a pain in the ass. Now, one way to hedge in Python, one way to hedge against making mistakes like that, now, Python won't enforce any of this for you automatically, but one way to hedge against making these types of mistakes is to have very good, well-documented code. Now, we learned about writing things like docstrings, right? And how you describe your function, describe what the inputs are, what the outputs are. And we have comments for our code to describe the code. And we also want to make sure our code is as self-descriptive as possible. Name your variables effectively. Name your functions effectively. Write it in a way that's simple and clear and easy to understand. But there's another thing that Python lets us do, where it's syntax that has no functional purpose, but it's syntax the programmers can use to encode additional information for other programmers and themselves about things like what the type should be. I think this is best explained with an example. Like, remember this example here? This is without type hints, right? If you don't remember, I'll run it. Here's a function. It takes A and B, and it returns the sum of those two things. So give me two numbers. First number 1, second number 2. We get back 12, obviously. Well, what the hell? No, it should be 3. Well, it's 12 because what did I do? I added strings together. This function really, I'm sure it worked, it didn't crash, but it was expecting integers, right? Or maybe floats, just numbers, not strings. So what we could do is add type hints. We can say, okay, parameter A, colon, float. Parameter A, it's a float. It should be a float, at least. Python will not guarantee that it is a float, but me as a programmer, you as a programmer, looks at the signature of this function. Oh, here's a function that takes two parameters, A and B. They're supposed to be floats, and the return type is a float. Why? Well, that's what the little like arrow float is. So now there's syntax that encodes additional information to other programmers and yourself about what the type should be. But for better or worse, Python will not enforce this for you. I can still run this and give it two strings, and Python will act as if the way it does. But here it's more clear. And you can even say, like, okay, our type is float, right, in the docstring. You can even add additional information to the docstring to describe what the hell all this is. Any questions about these type hints? We want our code to be good. Remember, Python code is for humans, not computers. We write self-descriptive code all the time. You want your functions to be named well. You want your parameters to be named well. You want to specify what the types are as much as possible. You need your docstrings. You should have comments. Your variables should be, everything should be written in a way that your code is as clear as possible. And as soon as you say, well, I wrote this code, no one's ever going to use it, I don't need to be that, no, you've already messed up. Because that's the famous last words. And if you go to Google and type in like, I don't need to comment my code, you're going to find a billion memes about like that. Don't make yourself the butt of the joke. Write good code. And when you do this, what you get is things like, look, in Colab, if I go back here, let's go here. Oh, well, okay, 2, okay, great. It still gives me back 22, so it didn't enforce anything. But like it does things like if I call add together, like look, it says, oh, add together. A, it should be a float. B, it should be a float. Like it shows you this stuff. Now, be warned that this little like pop-up window here, it's not, like this isn't a Python thing, this is Colab. Because you wrote your docstring effectively and you use type hints the right way, Colab could look at your code and give you a little bit more information about how you're using it, which is a good thing. If I have a moment here, I'm going to try to open this up. Now, I showed a lot of you this in lab already, but I'll see if I can show you again real quick. I'm going to load up Java, which is a different programming language, but Java is very strongly typed. And here, in this silly example, I've got the function down here. You know, the syntax is a little different, but chances are you can kind of make a sense of what's going on. Here is a function called density that takes a float mass and a float volume. And it's supposed to return mass divided by volume, and we return the value. Its type is a float. So the way we do like the typing is a little different than the type hints in Python. Here we put the type before the name of the variable. And instead of instead of a little arrow for the return type, we just put the return type out in front of the name of the function. But you know, we got this variable d, it's a float, we have to specify. Mass divided by volume, store it in the variable d, return d. And here I'm calling it. And before I even hit run, before I even hit compile, so unlike Python, Java, you've got your code, you have to turn the code into something the computer can run, and then you run that thing on the computer. So in Python, you can kind of skip that step and just run your code directly. It's weird. I'm not going to get into it. But even before I hit run, even before I hit compile, you can see it's telling me, like, what the hell are you doing? Mass is supposed to be a float. You gave me a string. Volume is supposed to be a float. You gave me a Boolean. I can't do that. Python ran and operated weirdly in a way we didn't expect. I mean, it did what we told it to. It's just we accidentally added strings. Here, I can't even run it. It won't allow me to even make that mistake. I try to hit run. It's not even that it runs and crashes. It doesn't even get to the point of running. It won't even try. And that is a good thing. For better or worse, though, we don't get that in Python. The only reason I'm bringing that up is sometimes programmers with some experience with strongly typed languages assume Python will enforce those types. It doesn't. It's just syntax to tell programmers what it should be. It won't force it, though. Yeah, okay. What you don't get, yeah, it'll still let you make that mistake. Cool. Any questions about the testing or type hints? Everyone's happy? Wonderful. All right, if else. Well, I kind of spoiled a little bit. And chances are anyone in here with some programming experience is already familiar with these ideas. But if I were to give you 2 minutes, 3 minutes, here's an activity. Using only what we have learned so far, so no using anything we haven't seen yet. Write a function, smush, that checks if if the number is positive or negative. If a number is positive, the function will return half of the value of a number. If the number is not positive, it just returns a number. So try to write that function. You know what? We can skip it because you can't. You can't do it because your code would need to be able to make a decision. All of the code you've written so far was very like, do this, do this, do this, do this, do this. But now we're getting to a situation where we're going to hit a fork in the road. If it's positive, I want you to do this. If it's negative, I want you to do that. We need a way to control what code runs based on some condition. We need an ability to decide something and then make and act upon that decision. And until now, we haven't been able to do that. We've been able to do variables, we learned about types, we learned about Boolean expressions, we could check if things are true or false, but we have no way to control the flow of the code. If negative, or if positive, divide the number by 2 and return that value. Or if it's negative, just return that value. We have to be able to make a decision, which we can't yet. But we're about to learn how. So we used Booleans to check if something was true, false, right? We learned about a couple of different operators. We used about comparison operators. And we also learned about Boolean operators like and or and not, right? So we have a couple of new tools, but we can use these operators to do a little bit more. They allow us to evaluate, we can do more than evaluate just true or false. With the true or false, we can start to do a little bit more. So here's the code. I'm going to take smush. I'm going to get rid of the doc string for brevity. What do we say? So to be clear, does anyone know how many ways there are to solve a problem? There's an infinite, literally an infinite number of ways. So if at any point, and here's the thing, we've learned enough now that you might look at my solution and you might say, I wouldn't have done it that way, I would have done it another way. Great, good, probably, because there's literally an infinite number of ways to do it. So if you look at my solution, you're like, I don't like that, I'd do it a different way. That's fine, you're normal. This is just one of the infinite number of ways to do it. So def smush, a number. It takes a float and it returns a float. I start by saying, okay, return value is going to be equal to the value I pass to the function. Okay. So if I give this function 7, return value takes on the value 7. Okay. -7, -7, whatever. Then I say, if a number is greater than 0, meaning it's positive, right? If it's positive, take a number and divide it by 2 and store it back into return value. Then, either way, after that if runs, and notice the code gets indented again. All of the indented code under that if is within that if condition. That code only runs if that condition is true. So if, in fact, the number is greater than 0, a number gets divided by 2. Then we unindent, because there's no more lines after indented in that if statement, so we go back to line 5. And regardless of whether we changed return value or not, we return value. Just have a look at this code and think about it for a moment and try to make it make sense. You've never seen an if statement before, but I'm willing, if you've never seen an if statement before, I'm willing to bet you can kind of make sense of what's going on here. Oh, I'm not frozen yet. Hey. Here, I'll go back to this one. It might be a little nicer. Any questions about this? Thoughts, concerns, comments, observations, points, notes, anything? And there, of course, I have my tests. Positive number, negative number, 0. That's probably sufficient for the tests, assuming a reasonable person wrote the code. If you're confused, the trick is, what does the code say? So let's just run through the values of where the tests are. I call smush with the value 10. Now everyone pay attention, wake up, and work with me here. When I call smush 10, what value does the parameter a number have? Everybody. Don't make me be like, come on everybody, just freaking do it. What is the value of a number? 10. I can end class right now if you want. If you don't know that it's 10, one of two things has happened. Either you're like, apathy's cool still. Yeah, man, you know it. Yeah, it's got bad news for you. It's not, and it never was. Or you don't know. Either way, we got a problem. If you don't know that it's 10, you're in trouble. If you know that it's 10, but you're too cool, what are you doing here? Last try, or I'm legit gonna leave. I even just told you the goddamn answer. When I call smush 10, what value does a number have? 10. Hey. Then, line 2 runs. Return value takes on what value? 10. All right. I'll see you later. Hope you enjoy your 13-minute break.